Okay, guys, we are getting started with Unit 3. So we are, well, not halfway through. We're 1/3 of the way through the course. We have 6 units in the course. We're approaching the halfway mark. We are shifting gears from polynomial functions, which is what the first third of the course was pretty heavily centered around, and we're going to shift to rational functions. But as you'll see, a lot of those concepts that we learned in Unit 1 and 2 are going to carry forward into Unit 3, even some of the factoring concepts and solving and things like that. So bear with me today. This is a bit of an intense lesson. It is setting the foundation. We're learning about a lot of new things that we haven't talked about yet in this course, and a lot of words, a lot of definitions, so just stick with me, okay? So for Unit 3, Lesson 1, we are going to start with the reciprocal of linear functions. We're going to talk about what that means, what is a reciprocal function, how is it a type of rational function, and by the end of this lesson you should be able to determine key aspects of the reciprocal of a linear function, including asymptotes, intervals of positive and negative function values. Actually, this list could go on, domain, range, intervals of increase, decrease, etc. So let's just leave it to I'm able to determine key aspects of the reciprocal of a linear function, and we will get the exhaustive list as we go through. So right away, let's just start with looking at a linear function. So create a table of values for the integer x values on the interval -2 to 5 for the linear function f of x is equal to x minus 2. Then draw a sketch of this function. This is just, a lengthy, a wordy way to say sub in x values from -2 to 5 and then create a graph to match this. So here we're looking at x, and here we have f at x, and in this case we're saying f at x is equal to x minus 2, and we're subbing in x values the interval -2 to 5, and integer values, meaning we're just going up by our increments of 1. So -2, -1, 0, 1, 2, 3, 4, and 5. And so when we sub in -2 minus 2 is -4, -1 minus 2 is -3, 0 minus 2 is -2. This is a linear function, so the first differences have to be constant, so it's going up 1, up 1. So we can just continue this pattern to figure out our remaining values. So there we go. We've got some values that we could then put on our Cartesian to graph or sketch this function. So when x is -2, f at x is -4, so we've got a point here, and then we go to -3. When x is 0, we have -2, and we have this 1, -1, 2, 0, so on and so forth. I'm going to use my line tool to draw a sketch of this function, which both ends should be an arrow, and we'll just use green. So we're going to go, oh, that's a little one. That's okay. And it should go through every box because the rate of change of this function is 1, right? Our slope is 1. It has an m value of 1. So it looks something like this. Okay, so there is the sketch, or the actually graph of x minus 2. So now what we're going to do on the next slide is we are going to create a table of values. And sorry, I said 5 key points. I had actually changed that of, let's just say, the key points for the same x values. So we're going to start from -2 and go to 5. But now we're looking for the reciprocal of f at x is equal to x minus 2. So before we do that, I just want to make a little side note down here of what is a reciprocal. And so hopefully you remember from fractions what a reciprocal is. So for example, if we have the fraction 2/3, the reciprocal of that fraction is 3/2. Okay, so basically it just means to flip. And what is important is that the product of reciprocal functions or reciprocal numbers always has to equal 1. And so if we have 2/3 and we multiply it by 3/2, 2 times 3, let's get rid of that equals 1 for a minute. 2 times 3 is 6, and 3 times 2 is 6, and 6 divided by 6 is 1. So if the original function that we are looking at is x minus 2, technically we know that any whole number, like anything, can be written as a fraction as over 1, and we've not changed it. So if this is the original function that we were looking at, the reciprocal of that function would be 1 over x minus 2. And again, to make sure that it follows that rule, if I was to multiply these, I would end up with x minus 2 over x minus 2. And as we know, anything divided by itself is just 1. So by definition, that is what the reciprocal is. Essentially, you can just think of like, I just have to flip it. It's hard when something doesn't already have a denominator, like the function x minus 2, but remember that anything can have a denominator of 1 without changing it, and then we flip and we don't have to do this double check, but just by definition, reciprocals have a product of 1. Okay, so for this here, now we're looking at creating a table of values and then ultimately a sketch for the reciprocal of x minus 2. So now f at x is going to be, sorry, I'm going to actually not write that like that, because if f at x is the original function, let's say the reciprocal is going to be g at x. So g at x is actually 1 over f at x, because it is the reciprocal, which in this case would be 1 over x minus 2, and then this is x, and our x values we're dealing with -2, -1, 0, 1, 2, 3, 4, and 5. So now, really what we're doing is we're taking all of these f at x values and putting them over, or under, sorry, 1, right? If this is f at x and if g at x is 1 over f at x, then the corresponding value here would be 1 over -4. Now we could sub in and we would get that same thing. We would have -2 minus 2, which is -4. So as we go through, and I didn't leave a lot of space here for all of the rational numbers that we're about to get, but again, I could just take all of these and know that it's going to be 1 over. So this is going to be 1 over -3. This is going to be 1 over -2. This is going to be 1 over -1. I'm just staggering them, sorry guys, which is -1. This is going to be 1 over 0. We can never divide by 0. That gives us an error. We'll talk about what that means. That's happening when x is equal to 2. Then this is going to be 1 over 1, which is just 1. And then this is going to be 1 over 2, which is a half, and 1 over 3. So sorry, those are not lined up very well, but these are the values that we are dealing with as we are going up by 1 on our x-axis. So when x is -2, my f at x, my function value, my g at x actually, but y, you guys get the point, is 1 over -4, which is just -1/4, which is -0.25 for those of you who hate fractions and love decimals. So it's about a quarter of the way down here. And then we go over and we have -1/3. So it's just a little bit further. This should actually be up even more. It's really hard to graph some of these values, and you'll see that, you know, what kind of happens on our graph, but we'll put this here a quarter of the way, and then we'll put this a little bit further. It shouldn't quite be half, because at 0 we have -1/2. We'll do our best. And then at 1 we have -1, so we have this value right here. And then something happens here at 2, and it's an error. That means we cannot sub an x value of 2 into this function. We are never allowed to divide by 0, and if I put a 2 in here, I will be dividing by 0. Under no circumstances can I put the number 2 into this function. This number is off limits. And you might recall what happens when a number is off limits, but when we are dealing with functions and rational functions specifically, when we have a number that is off limits, we put a vertical asymptote there on our graph to say, nope, I can't sub in x equals 2, which means there is no way that my function should be crossing this line at any point. There is no function value that corresponds with an x value of 2, because I'm not even allowed to sub x equals 2 into this function. Okay, so then I go back and I look at my other ones. When x was 3, I have a function value of 1, which is up here. And when x was 4, I have a function value of 1/2. And when x is 5, I have a function value of 1/3, so a little bit lower than that. Okay, so you might be wondering, like, what is going on here? And I'm going to show you what this looks like, but also you can see that it's curving up this way, and also that it's curving down this way. And do my best to draw this. It's going to look something like this. And also something like, we got to go through that point. That point's important. Whoop. Okay, that's not pretty, but I'm going to show you I have a picture of it properly on the next slide. Okay, so based on our table of values, this is what the reciprocal of x minus 2 looks at. So let's get rid of that. Let's look at this nicely. So here we have the original function. So the red line is our f at x is equal to x minus 2. And then the blue line is our g at x, which is equal to 1 over f at x minus 2. And the blue is, we'll call it g at x, which is 1 over f at x, which is 1 over x minus 2. Okay, so we've got this reciprocal function and the original function graphed on the same Cartesian so that maybe you can see what you notice about the two graphs. So right now, you might pause this video and just really take a look at the two and see what you notice, what you wonder. This slide is definitely more beneficial to my in-person students who can actually turn and talk with people, but maybe if you're working with someone, you could chat with them for a minute right now. And when you're done, just come on back and press play. Okay, so hopefully you took a minute and you took a look at this video. And some things you might have noticed is this obviously vertical asymptote, right? We have this vertical asymptote, we'll call it a VA, vertical asymptote, and it's happening at x equals 2. And that also happens to be the x-intercept of the original function, okay? So that might be something you noticed. That's not a coincidence, okay? Something else you might have noticed is that the two functions intercept here and here. So they intercept at 3 and 1, and at -1, -1. That also not a coincidence. We'll talk about why those point of interceptions are where they are, and why we can come to expect to see those point of interceptions for any reciprocal functions. Maybe not at that exact same place, but you'll see what we mean as we move through. You might have also noticed that when the original function, okay, so the red line, whenever that function is above the x-axis, so here's your x-axis, anytime that function is above the x-axis, the reciprocal function is above the x-axis, and anytime that function is below the x-axis, the reciprocal function is below the x-axis. So again, that's not a coincidence, and when a function is above the x-axis, it has positive function values. So that means that both f at x and g at x have positive values or positive function values on the same intervals. Okay, positive, we'll talk about this as we move through, but positive function values on the same intervals. If f at x is positive, g at x is positive. If f at x is negative, g at x is negative. So there's a few things going on here. Maybe you notice a few other things, but let's just start jumping into the specifics and how these two graphs relate. So, of course, we can talk about asymptotes, and this graph actually has two asymptotes. We already paid attention a little bit to the vertical asymptote, which was happening at x equals 2. So let's draw that back on there. Oh no, that's annoying. Okay, at x equals 2, we had a vertical asymptote. But you might also notice that there is a horizontal asymptote at y equals 0. And so there's two imaginary lines that are controlling the shape of this function. This function is being forced to go up, 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 because it can't go past this point. And it's also being forced to go down, down, and this way, and it can't go past this line. So those are our asymptotes. And so here we have a vertical asymptote, and here we have a horizontal. And what is important to note is that vertical asymptotes put limitations on the domain. So often when we think about vertical, we associate anything vertical with our y values. What we know is that domain is the permitted or not permitted x values of a function. But the vertical asymptote corresponds with an x value. Okay, so vertical asymptotes put restrictions on our domain. Horizontal asymptotes correspond with a y value, and therefore they put a limitation or a restriction, I guess we should actually maybe call it, on the range. Okay, so for this graph that we created, state the domain and range for the following rational function. So we're not looking at this red line. That was the original function that's just graphed on the same Cartesian. But for the rational function, and note that the rational in this case is the reciprocal, and we're calling it g at x is equal to 1 over x minus 2. And this here is what makes it a rational function. Having some polynomial in the denominator. Remember, our definition of polynomials was that all the exponents on x had to be positive. This technically has a -1 exponent on it, and so that makes it not a polynomial and instead makes it a rational function. So domain and range of this function. Well, for this function, g at x, x is an element of the real number system such that, so if we look at all our x values, x can be anything it wants, but it cannot be 2, such that x cannot equal 2. And the range of this function, and especially given the graph of this, there is no way for this function to have a function value, a y value of 0. So we could say y, or we could say g at x. It doesn't matter. Let's say g at x is an element of the real number system such that g at x cannot equal 0. Okay, this function can never equal 0. We have a horizontal asymptote at y equals 0 or at g at x equals 0. Okay, so we must be able to state the domain and range for our rational functions, and as we move through this unit, we will not always have the graph to state the domain and range, which means we're going to need to be able to look at this and just from looking at this know, okay, well, I can't ever put an x value of 2 in here, and I can sub in pretty much anything I want and get back any function value, but I'll never get back 0, because the only way for a rational function to have a function value of 0 is for the numerator to be 0, and we're going to talk about this later in this lesson. But 1 divided by literally any number is going to give you back a number that's not 0. We can't divide by 0 to get 0 because this is a math error. The only way when we have a quotient or division, the only way to have it equal 0, so to have a quotient of 0, is if the numerator is what turns to 0. So we can have a 0 on the top, but we can never have a 0 on the bottom. 1 divided by anything is never going to equal 0, so we know that this is never going to have a function value of 0. Okay, asymptotes continued. So a vertical asymptote exists because the function can never allow these x values. We've already talked about this. Y, we can never divide by 0. We can never sub in, and the way you can always solve for it too is to say, okay, I can never allow x minus 2 to equal 0. So what is the x value that would make it equal 0? And then again, we use our opposite operations and we figure out, and this one's pretty easy. We know x cannot equal 2, but if the denominator was not so pretty, if it was, maybe a quadratic or a different polynomial, we might need to actually do some solving here. So vertical asymptotes exist anywhere essentially where we have the risk of the denominator turning into 0. We can never divide by 0, so we got to throw up a vertical asymptote and say nope, not going to be that x value, not now, not ever. Okay? Horizontal asymptotes exist because we can never provide that function value. Okay, so opposite to vertical asymptotes put restrictions on our domain. They are x values that are not allowed, that our function cannot accept, and horizontal asymptotes are function values that are just never possible. We are never going to get back that value. And why, we already talked about this. The only way to get a function value of 0 is if the numerator is 0, but in a reciprocal function, the numerator is always 1. So we will always have, every time you are dealing with reciprocal functions, meaning you've taken some function and inverted it and put it under a numerator of 1, there will always be a horizontal asymptote at 0, at y equals 0. I guess I don't have it written here. Okay, so at y equals 0, you will always have a horizontal asymptote when we are dealing with reciprocal functions. This is not for all rational functions, okay? So, in general, for all rational functions, meaning some combination, some quotient of polynomials. Actually, let's go back and release those one at a time. Vertical asymptotes can never be crossed. Okay, so if there is an x value that is not permitted, it is never permitted, ever, ever. Okay, there is no situation in which we can have an x value of 2. Horizontal asymptotes can sometimes be crossed. Okay, in this case, it can't be. We can never have a function value of 0 because it's just not possible, because we can't divide by 0 and the numerator is not 0. But what if we were dealing with a different rational function, and we're going to get to this in a couple lessons, but what if it was x minus 2 divided by x minus 3, for example? Well, is there anything that, or even, no, I don't want to go too far ahead without teaching this stuff, because we do have a whole lesson of linear over linear rational functions. But just note that sometimes it's, this value is never possible, or most of the time, but there is one exception in which we can cross that horizontal asymptote. So we will look at examples, but just for right now, just know that sometimes horizontal asymptotes can be crossed. If the degree of the numerator is less than the degree of the denominator, there will always be a horizontal asymptote at 0. So here, the degree of the numerator, this is technically a degree 0, and this would be a degree 1. Okay, so we have a degree 1 and a degree 0, or just a constant. If the degree of the numerator is less than the degree of the denominator, there will always be a horizontal asymptote at y equals 0. However, it might be crossed when the numerator is not a constant. If the numerator is a constant like it is here, it won't be crossed. But if we were dealing with, let's just say this example here, but this was like this, the degree of the numerator is less than the degree of the denominator, there might be still that horizontal asymptote, but it also might be crossed. We will investigate all of this later, guys, so I'm just, because we're introducing this idea of asymptotes, I like to just make it clear from the beginning that when we're looking at rational or reciprocal functions, both vertical and horizontal asymptotes can exist. Vertical asymptotes can never be crossed, never, ever, ever. You will see some examples throughout this unit where horizontal asymptotes are crossed. As we come to those unique situations, we will talk about them, okay? Okay, another thing you might have noticed when I put this up and said, tell me what you noticed, and you might have noticed these points of intersection there. And so oh, sorry, I'm jumping ahead. Let's talk y-intercepts. No, I'm going to do the shared points first because I already introduced it. Okay, so those shared points, those were the shared points that we saw. So a function and its reciprocal will always share a common point wherever y was equal to 1 or y was equal to -1. Okay, so in this case, in the red function, y, or our function value, was equal to 1 when x was equal to 3, and notice that that was the exact same case for the reciprocal. And in our original function, the red function, y was equal to -1 when x was equal to +1, and that was the exact same for the reciprocal of that function as well. So why does this happen? Well, remember that the reciprocal is 1 over the function. So we can take the function value, which is f at x, and put it under 1. If we do 1 over 1 or 1 over -1, this is still just equal to 1. This is still just equal to -1. If this was the original function value, right, because it's 1 over f at x, if we put a 1 on the bottom, we still just get back a 1. If we put a negative 1 on the bottom, we still just get back a negative 1. So reciprocal functions will always have those shared points, those 2 points of intersection at wherever the original function had a function value of 1 and when the original function had a function value of negative 1. Okay, so hopefully that makes a little bit of sense. If you remember back to the table of values, this was the original table of values, -4, -3, and we said to find the location of when x is -2 for the reciprocal function, we're just doing 1 over -4, 1 over -3. Well, notice how this here, 1 over -1, 1 over f at x is still -1, and here 1 over 1 is still +1. Whereas for all the other values, it significantly changes it because 1 over 2 is a half. That is not the same as 2, right? 1 over 3 is a third. That's not the same as 3. So this only remains true for when the original function had a function value or a y value of +1 and -1. The reciprocal will also have a function value at those same x points, and then that becomes the 2 shared points of the original function and the reciprocal function. This one really allows you to start drawing your reciprocal function graphs with a little bit more accuracy. If you have your original function on the Cartesian, you know I got to go through this point here because they have to intersect at that point. Okay, y-intercept of reciprocal function. So keeping with this idea that a reciprocal function is 1 over the original function, so 1 over the function value, then this should make sense that the y-intercept of a reciprocal function will always be 1 over the y-intercept of the original function. So if here our original function had a y-intercept at -2, okay, so f at x had a y-intercept at -2. So 1 over f at x will have a y-intercept at -0.5. Okay, it's 1. We'll write it as y-intercept at -1 over 2. It's the reciprocal. It's 1 over -2, which is -0.5. And again, this is going to be true for all reciprocal functions. It's just 1 over the y-intercept, and that will be another thing that will help you draw with a little bit more accuracy. Okay, intervals of positive and negative function values. So whenever the original function has a positive function value, the reciprocal function will too. So again, I had said that earlier, that might have been something you noticed, that anytime that the red function is above the x-axis, the blue function is above the x-axis, and as soon as the red function drops below, the blue function drops below. Again, not a coincidence. Anytime the original function has positive function values, the reciprocal will too. Whenever the original function has negative function values, the reciprocal will too. So why is this? Well, 1, because remember the reciprocal is just 1 over the original function values. 1 is a positive number, so if the original function value was positive, and 1 is a positive, the reciprocal is going to be a positive. If the original function value, so 1 over f at x, if the original function value for some x value had a function value that was negative, 1 over that negative is also going to be a negative. So anytime the original function is positive, the reciprocal will be positive. Anytime the original function was negative, the reciprocal function will be negative because the numerator is always 1, which is a positive, and that doesn't impact the positive or negative value. Okay? So that's important. Again, that will really help your sketching of these functions. Okay, one last important thing, and then we'll kind of summarize all of this, and then I'm going to pause this video and come back to do some examples. So intervals of increase and decrease, which is also our rate of change. So remember this original function, and I added a second one here, but this is the function we've been looking at the whole class, is this red line. This has a positive rate of change the entire time. There is no turning point. It's a linear function. So this function is increasing the entire time. Notice that the reciprocal function is decreasing the entire time. On this, it has 2 portions because of the vertical asymptote. Here, the y values are getting greater and greater, or the function is going down, 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 down. And here, anytime we're moving from left to right, the function is going down, 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 down. And on our original function, it's going up, 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 up. Okay, so on intervals where the original function has a positive rate of change, or is increasing, the reciprocal function will have a negative rate of change or will be decreasing, and vice versa. Okay, intervals where the original function is negative or decreasing, the reciprocal will be positive. So why does this happen? Remember that the reciprocal is 1 over f at x. So as f at x, as the function values get really, really, really big. So if we were looking at this original graph, as we are looking at large, large, large positive values, like here when f at x is 10, if we do the reciprocal of that, we're looking at 1 over 10, which is 1/10, which is so, so, so tiny. So basically, they're all flipping places. But also, as the original function values get really, really, really small, so if down here we're looking at like 0.25, let's just say, because I know you guys love decimals. When the original function is 0.25, the reciprocal is 1 over 0.25. 1 split into quarters is 4. So when the original function has small values, we get back bigger reciprocal values, which means they kind of flip places. When the original function has large values, like here would be 10, the reciprocal is going to have really, really, really small values, okay? And so the result is when the original function is increasing, the reciprocal is decreasing, and vice versa, okay? So let's just quickly summarize everything we talked about here, and then I'm going to pause this video and we're going to actually do some examples because this is a significant amount of information. So when we are given some function f at x, we should be able to determine all of the following for g at x, which is 1 over f at x. In other words, we should be able to determine all of the following for the reciprocal of that function. Okay, so reciprocal of the, let's just call it OG function of the original function. Okay, so we should, when we are given any function, be able to determine the domain of the reciprocal of that function, the range of the reciprocal of that function, the y-intercept of the reciprocal of that function, the location of any asymptotes, vertical or horizontal, okay, so vertical or horizontal, and the behavior at those asymptotes. We didn't talk much about that. We will talk about that as we move through, because just because we have a horizontal asymptote, or sorry, a vertical asymptote here, how did we know that the function was going like this? And even with a horizontal asymptote here, how do we know that the reciprocal function looked like this and not like this? Okay, and there's ways that we know, but we need to make sure we have the right behavior. How do we know that on the right side of this asymptote it's approaching positive infinity versus approaching positive infinity on the left side of that asymptote? How do we know the behavior? How do we know that the function is above this horizontal asymptote and not below, etc., etc.? So we will look at that as we go through our examples, but we should be able to determine the behavior of the function at the asymptotes. We should be able to determine the intervals of positive and negative function values. So in other words, when is the reciprocal function above the x-axis, below the x-axis? And we should be able to determine the intervals of increase and decrease. When does the reciprocal function have a positive rate of change versus a negative rate of change? As well as the end behavior, but actually we're going to we kind of already know the end behavior once we've investigated the behavior on either side of the asymptotes. So that's kind of a moot point when we're already looking at our asymptotes. So a couple key points that you might wish to jot down in your notes. When f at x is increasing, that should say, the reciprocal function is decreasing, and vice versa. Okay, so as one is going up, the other is going down. As one is going down, the other is going up. And we're talking about the rate of change when we say increasing versus decreasing here. When the original function, when f at x is positive, the reciprocal function is also positive. And And then, of course, the vice versa. When f at x is negative, the reciprocal function is negative. When f at x has an x-intercept, the reciprocal function has a vertical asymptote. Okay? Anywhere where the original function has an x-intercept, because if we're talking about the function x minus 3, this will have an x-intercept at positive 3, but the reciprocal of that function is going to be 1 over x minus 3, because we're flipping it, which means that the reciprocal can never have a function value at an x value of 3. Okay, so where an original function has an x-intercept, the reciprocal function has a vertical asymptote. Where f at x has a y-intercept, so where the original function has a y-intercept, the reciprocal function's y-intercept is 1 over, how am I going to write this? The original function's y-intercept. I guess we could say 1 over f at 0. Y-intercepts always happen when we have x value of 0. So the original, this would be the original function's y-intercept. The reciprocals will be 1 over that value. So if the original function has a y-intercept at, let's say, 3, the reciprocal will have a y-intercept at 1 over 3, 1 over that value. The reciprocal of a function will always have and we're talking about reciprocals here, okay, so just reciprocals will always have a horizontal asymptote at y equals 0. This is not, that doesn't say asymptote. This is not for all rational functions, but it is the case for reciprocal functions because reciprocal functions have that numerator of 1, and the result is always going to be a horizontal asymptote at y equals 0. And the last point here, the reciprocal of a function will always share 2 points with the original of that function, and those 2 points will be anywhere or whenever the original function had a function value of 1 or negative 1, and at those same corresponding x values too, same x1, x2, okay? So this is a lot of information, but this is everything we've done so far. This video is getting quite long. Basically, I'm going to stop this, and when we come back, we're going to just do 2 examples to see how this all looks when we are actually graphing the reciprocal of a function. Okay, come on back for video 2.